G'day. In the 1500s, the Italian mathematician Tartaglia described a problem which became the forerunner of a whole class of problems in mathematics. And the problem was a fairly simple one. Given two empty and unmarked containers, now litres hadn't been invented then, but let's call them 5 litres and 3 litres. The challenge was, given a tub of water, to measure 4 litres. Now, to give you an idea, you could start by filling the 3 and pouring it into the 5 and filling it again and pouring it in, and of course now we would end up with 5 litres here and 1 litre here. I'm not sure that these are the exact measurements, but I just wanted to show you the idea. Some of these have a 4 and a 9 litre container to measure 6 litres, or a 3 and a 7 to measure 5, or something like that. And I'm intrigued to see whether you can work out, before seeing the explanation, how to measure 4 litres given a 5 and a 3 litre container. And I suggest you pause the video and try to solve it before hearing my solution, because mathematicians developed a rather intriguing and clever way of solving these problems, the whole class of them, and it involves drawing graphs. So wait on if you want to see the solution. Well, I'm glad that you have waited long enough to see the explanation. Let me encourage you, before I go on with this, to Google this man's name. Whoops. Tartaglia. It's not really a real name, it's a nickname. And this gentleman, who lived in the first half of the 1500s, is one of the, well, I suppose he's sung a little bit, but I think he needs to be sung a lot more loudly. A hero in Italy, an Italian mathematician of great stature. He was the first to write a book on ballistics. He was the first to make major breakthroughs in the solving of cubic equations. Shared his ideas with Cardano, and that Cardano published under circumstances that he felt he had to rush, and there was a bit of a bitter wrangling went on, but the solution is called the Cardano-Tartaglia or Tartaglia-Cardano solution. But he's responsible, and quite a remarkable mathematician. And he was the one who came up with this idea of measuring with jugs. So how do mathematicians, I just wanted to say, please Google his name and learn a little bit about him. Fascinating man. And Tartaglia in Italian means stammerer. He suffered a very bad injury during a war, taking shelter, and a soldier burst into the cathedral where they were and slashed at him and slit his jaw and palate, and he never was able to speak properly since. But yeah, some tragedy, but a remarkable man, and self-taught, even more remarkable. So please look him up. A lot of great people in the history of mathematics. So let's get on to the jugs. Let's imagine we have a 5 litre and a 3 litre container, and a reservoir, if you like, full of water, and you can pour to your heart's content. Now, of course, there are no gradations, so you can't pour part of the 3 out or part of the 5. It has to be all or nothing. So you pour all of the 3 in there, or as much of the 5 as will fit in the 3, or you can pour back into the container. Here's how mathematicians analysed this problem and others. They would start, for example, by drawing axes and saying this is container number 1, and this is container number 2. And let's put some marks on for litres. 1, 2, 3, 4, 5. I'm going to make this the 5 litre container. It doesn't have to be. You could have the 3 and the 5 here, as long as they're different. And here's the 3 litre container. And just faintly, I'll try and draw the grid lines in. That first one wasn't very good. Let's see if I can improve on it. There we go. I hope you can see those. So let's try and understand the pouring. If we start with nothing in either container, we're starting here at 0. If I fill the 3 litre container by dipping it in and filling it right up, then I move to this position where I have 3 in the 3 litre container and nothing in the 5 litre container. So I can call this 3, 0 if I like, just the same as we do it on graph paper. If I instead fill the 5 litre container, I would fill this and regard this as 0, 5. 0 in the first container and 5 in the second. So that's what filling each container would be like. What would it look like if I poured water from one container to the other? Well, if I poured this 3 litres from this container into this one, then this 3 litres would end up in this container at the 3 litre mark, and there'd be nothing left in the first one. So in other words, it represents a diagonal line. Also, if I poured the 5 litre container into the 3, it would go like so to here, and you would see here that this is the point 3, 2, cross 3 and up 2, and it would represent 3 litres in the 3 litre container and 2 litres left in the 5 litre container. Let's picture that. There's your 5 litres, there's your 3, this is full. We pour it in, this fills up with 3, and this loses 3 litres and has 2 litres left. And that is describing this. 3 litres in the 3 litre container and 2 litres left in the 5. So in other words, pouring water from one container to another takes place upon a 45-degree angle. Filling either container is a vertical or horizontal line. So as not to perhaps confuse matters, or to indicate that pouring back into the container, which would be pouring back into 0, emptying one of these vessels, so that this pouring or pouring the other container is seen as equally valid, mathematicians then tilted the axes over to form not squares but equilateral triangles. So let me show you how they did it. It's not a great... we could do our analysis on the graph that I've drawn, but if you look in the books where people have analysed these things, they'll draw it this way. They'll have 1, 2, 3 litres in the container at the bottom, but they will picture equilateral triangles, and they'll draw an angle up here at 60 degrees. 1, 2, 3, 4, 5. I hope I've done this with some degree of accuracy. And this will test me out to see just how good I am at sketching, or how bad. And there we go. That's not too bad. So if, for example, I had the 5 litre container filled I could pour into the 3, or I could pour it back into the container at the bottom and just empty the 5 litre container. And you can see that both those options are equally valid and just as equally easy. And that's, I think, why they tilted these diagrams over. And you can see that this diagonal line now is one of these lines. So what's our challenge? Our challenge was to measure 4 litres. Here's the 4 litres. We certainly can't have 4 litres in our 3 litre container, but we could end up with 4 in our 4 litre container, and that is where we want to end up. And the challenge is how to do it. So you see, by the way, we could do this. We could fill the 3 litre container, pour it into the 5, fill the 3 litre container, pour it into the 5, and we've now got, at this point, 1 litre in the 3 litre container and the 5 litre container is filled. We could empty the 5 litre container, pour the 1 litre back into from the 3 into the 5, fill the 3 litre container and pour that 3 litres into the 5 litre container. You can see that we're limited to travelling on this hexagonal pattern, zigzagging around to get to here. We could have gone up here and down and back and down and up and down and across this way. You could look for a variety of paths. Those would be the 2 obvious ones. But just zigzagging on the diagonals to get to the 4. So let's rehearse this again. Fill the 3, pour it into the 5. So we've now got 3 litres in the 5 litre container. Fill the 3 again, pour it into the 5. So we've now got the 5 is full and the 3 litre container now has 1 litre left in it. We empty the 5 litre container. That's got us to here. We then pour the 1 litre into the 5 litre container. We then fill the 3 litre container and then we pour that 3 litres, this 3 litres, in onto the 1 litre in here to make 4 litres, 3 in 1 is 4 litres in the 5 litre container. It's these patterns that mathematicians devised to solve all this class of problem. As I said earlier, there are some where you've got, I can't remember off the top of my head, a 4 litre and a 9 litre container, and you're supposed to measure out 6, and there are a variety of others. And these have been invented all over the world. I've seen Japanese versions and Hungarian ones and English ones and all over the place. But they all have this common feature that if you draw a diamond grid or an equilateral triangle grid like this, filling one container is a horizontal line this way, filling the other container or emptying it is a diagonal line that way, and pouring from one to the other is a diagonal this way. And it's simply a matter of zigzagging from the boundaries around to get your result. And all of a sudden it becomes a game with patterns rather than a difficult mental exercise. But it's a fascinating insight into how mathematicians have tried to analyse a problem and understand the principles behind it, and then represent the pattern in the problem as a pattern in a diagram. And I love diagrams. I think this is a fabulous example, a wonderful example of how to make a difficult and perhaps even an intractable problem relatively easy. So you could go to town now and imagine if you had an 8 litre and a 17 litre container, or an 8 and an 11, or a 13 and a 21 litre container, how you would measure out 14 litres or something. And you might find that if you draw the diagram up on, particularly if you can obtain some ready drawn paper, you might have to zigzag quite a few times before you get a solution. And then of course the challenge is, how do you know it's the best solution or the shortest one? Therein lies another challenge. And I guess the further challenge is, I've seen puzzles like this that have 3 jugs or more. And of course this is 2-dimensional. So the problem becomes rather more difficult once it moves to 3. But anyway, I hope you have enjoyed that insight and can appreciate the simplicity. It looks complicated, but the simplicity of completely filling, completely emptying, completely filling, emptying, and moving around in such a diagram to solve what appears to be a difficult logical problem. Thank you for watching.